Welcome to the deep dive. Today we're getting into this really stunning new Hubble image.
That's right, of the Large Magellanic Cloud.
Yeah, the LMC. They're calling it a cotton candy-like cloudscape. Looks incredible.
That really does.
But we want to, look beyond just how pretty it is, understand the science behind it, what it's actually telling us about this galaxy.
Exactly. We're pulling from what NASA and the ESA have released about it.
And the intriguing part, for me anyway, is this idea that it uses light we can't even see.
Mm-hmm. That's central to it. It's not what you'd capture with, say, a standard camera. Hubble's showing us layers that are usually invisible.
Like seeing something familiar but different.
Precisely. Whole new perspective.
Okay, so let's back up a tiny bit. The Large Magellanic Cloud, the LMC, remind us, what is its relationship to us, to the Milky Way?
Sure. So think of it as our biggest neighbor galaxy, really. It's a satellite galaxy.
Meaning it orbits us.
Yeah, it's gravitationally tied to the Milky Way. It's actually relatively close, cosmically speaking,
Oh,
about 160,000 light years away.
Okay. Still mind-bogglingly far, but close for a galaxy.
Right. And you can spot it in the southern sky in Dorado and Mensa constellations.
So Hubble took this picture. You mentioned it sees things we can't. How exactly does that work? What's the tech?
Well, it's using its Wide Field Camera 3, the WSC3,
Mm-hmm.
and instead of just, visible light,
Like our eyes see.
right, it used 5 different filters. And these filters are specifically designed to pick up certain wavelengths, including ultraviolet and infrared light.
Which are completely invisible to us.
Completely.
Wow. Okay, so you have this invisible light data coming from Hubble. How do scientists turn that into this colorful picture?
It's a really neat process. Image specialists take the raw data from each filter. Remember, there are 5 sets of data, and they combine them.
Layer them up.
Sort of, yeah.
Yeah.
And then they assign colors to each filter's data to make it visible and, importantly, interpretable.
How do they choose the colors?
There's convention, usually. Shorter wavelengths, like UV, often get assigned cooler colors, blues, purples, and the longer wavelengths, like infrared, typically get warmer colors, reds and oranges.
So when we look at those blues or reds in the image, are those the real colors of UV or infrared light? I mean, if we could see them?
That's a good question. It's not quite like that. The colors are representative. They're a visualization tool.
Ah, okay.
It's not what your eyes would see because, well, our eyes aren't built for UV or infrared, but the color scheme is chosen very carefully to be scientifically meaningful.
Meaningful how?
Well, different colors or intensities often map directly to real physical properties, like maybe temperature differences in the gas or the chemical makeup.
I see. So it's a code, almost.
Kind of, yeah.
Right.
A visual code based on the physics. And, scientists could use different color palettes for different research goals or even just for aesthetics. But this way tells a specific scientific story.
Right, and that story seems to be the crucial bit. What information are we getting from seeing in UV and infrared that we just wouldn't get otherwise?
Okay, this is where it gets really powerful. Ultraviolet light, for instance, is strongly emitted by very hot young stars.
Ah.
So if you see bright blue or purple areas in this Hubble image, you're likely looking at intense star formation zones, nurseries packed with newborn stars.
Okay, that's cool. And infrared.
Infrared is fantastic because it can pierce through cosmic dust. Dust clouds normally block visible light, hiding what's inside.
So infrared lets us see through the dust.
Exactly. It lets us study cooler gas, the dust itself, and perhaps most excitingly, stars that are still forming, still wrapped up in their dusty cocoons. Things that are just dark patches in visible light suddenly show structure in infrared.
Wow. So this cotton candy look, the wispy shapes and colors that's telling us about these processes, starbirth, dust, temperature.
Precisely.
Yeah.
Those textures and hues aren't random. They're visual cues. The blues showing hot young stars, the reds maybe showing cooler dust or embedded stars revealed by infrared. It's mapping the complex physics going on inside those clouds. The wispy look itself likely shows how gas and dust are being pushed around by stellar winds and radiation.
That's incredible. So just by extending our vision beyond the visible spectrum, we get this much richer, more complete picture of what's happening in the LMC. It's not just a pretty picture, it's packed with data.
Absolutely. That's the power of instruments like Hubble. Observing across the electromagnetic spectrum unlocks details about cosmic evolution, star formation, the whole life cycle of galaxies, really. This LMC image is a fantastic example.
It really makes you think, doesn't it, about how limited our own senses are?
Yeah.
If looking in just UV and infrared reveals all this extra detail about one galaxy, What else is out there? What invisible processes are happening all the time that we just can't perceive?
That's a profound thought. How much of the universe is hidden simply because our biology isn't tuned to detect it?
Makes you wonder how different our whole understanding of reality might be if we could see more. A truly mind-bending thing to consider. Thanks for walking us through this amazing image.
My pleasure. It's fascinating stuff.